It keeps on can't keep unemployment away. A video about it might make you a hit. We are 20% through, and we are moving on ahead, charging ahead with this problem. Schedule tasks on minimum machines. So given n tasks, implement a task scheduler that finds the minimum number of machines required to complete these n tasks. So it reminds me of those merge interval problems we evaluated a while ago. And it's similar in quite a few ways. It's just that this time we're going to use a heap, well, two heaps, the two heap pattern. Um, a heap is also called a priority queue if you're coming from like other languages where priority queues are part of the standard library. So we have these tasks start and end times. So 1, 7, 8, 13. And we need to find the minimum machines required to execute them. Now, when there's overlap, we know we need a new machine in the task because one task has to end before another can be done with that same machine. So one machine can do these two tasks, but notice that this falls within here. So you need two machines because this happens at the same time with this. So you need two machines. Similar with this and this, there's overlap, but there's none here. So still two machines. And then these three one machine can handle these three. One machine can handle these three. That's why we have two machines. I believe that makes enough sense. And we can jump right into the solution to this problem. Again, we're evaluating the two heap pattern, like overarching pattern for these problems. And the solution is interesting. And I think I'll jump between the code and this diagram. So first of all, you take everything and put it inside this heap, sorted by the start times. Is it the start times? Yeah, the minimum heap, minimum machines. So everything is put in here, this minimum heap. And that is, so we have this function tasks. We're going to return this value, ultimate machines. We create a few heaps, right? This is the task list. So every single task, we put it into a minimum heap. And that is what we've done here. Order of incoming tasks. Measures the earliest end time. So and another heap machines available. It stores the earliest end time. So this one's based on end times. And I think this is based on start times, right? This is the heap, the minimum heap. So the earliest start time is on top, while here the earliest end time is on top for the machines available. And we also keep a number of machine counts for this heap, and you'll see as we move forward in the problem. So we pop from the list. So this is a task with the earliest start time, and we then allocate one machine, right? So we keep that in this heap as well. But this heap, the property we're using to maintain the heap, the minimum heap property is the end time, right? But we also store the machine count in there. And so we have this task, it's put in here, it uses one machine. Then next, number five comes out because this is the next earliest end time, right? So this is a minimum heap by the start time. Sorry, not end time, by the start time. This is a minimum heap by start time. This is a minimum heap by end time. And we take the next thing, 5 and 6, because 6 is before end time, we end up having to increment the machine. So now we have two machines. Yeah. Then up next, 6 and 7 will be next. And now, because 6 is right next to this, you don't need a new machine, right? You just update the end time here. We get 7 and 2. That's it. And you just keep going. That's all there is to it. You pop this 8, 13, 8 and 13. The end time is 7, but the start time is after both of them. So it can pick any one of the machines to do what it needs to do. And we're still at 2 machines in total. So we do 10 and 14. So 10 and 14, it's 7, right? You can replace the 7 because 10 comes after 7. And actually, this end time is supposed to have 7 on top. Yes, that's what happens. 7 is on top, so it's comparing 10 to 7. It comes after, so it replaces this guy. And that's it. We are done. So we only needed 2 machines. And this is what this process looks like in code. The machines available as this heap. We have the task lists. So the minimum heap made of the list of tasks that we passed into this function over here. And then we keep a tally of what machine is in use in particular. And machine in use actually looks like this. It keeps a task, the end time of a task, and the count, the machine count so far. So while there's something in this heap, that's what this while loop is doing. We take the first thing out, right? Just like we did here. We took 1 and 7 out. And okay, if machines available, right, has something, if there's something in machines available, and this task, whatever we just took out, the start time is after the end time from machines available, then we can take it out and replace it on the current machine. So that's what happens when, for example, these two, this needs a new machine. However, when 6 and 7 comes in, there are machines available actually, and the current task start time 6 is greater than or equal to what's on top. 6, right? 6 is on top here. So what we're gonna do is kick this out, what's on top, the pop, and replace it with what's here, only 7 and the machine number, right? So you can think of these as machine IDs, pretty much like a sequential ID of a machine. And so whatever ID it had, in this case 2, we'll replace it. So that's why we now have 7 and 2, like so. And it's a heap. So when you popped it and replaced it, you came down here and pushed that new thing you just created onto it, so it rebalances itself and like moves down in this case, like so. On the other hand, like in the first case that we evaluated, if this isn't so, let's say there's nothing in the machines available yet, right? There's no machine in use right now, and there's no task to even compare to, right? Because again, there's no machine here. And I think this short circuits, that's why this doesn't even error out, right? You can index it here because this short circuits, it sees that this is false already, so it doesn't evaluate this. If there is a conflicting task, increment the counter for the machines and stored in the end time on the heap of machines available. So optimal machines gets incremented by 1. And in this case, for the first time, it goes incremented from 0 to 1. And we store machine in use, like so. And then we push it, as always. And when we're done running through this whole process of like emptying this out, we come down to here where we just return the machine, and that's all there is to it. I think this is a medium problem on LeetCode, so not too bad. The previous problem was a hard problem, and I need to be keeping track of that as I make the videos so that I know what to expect, like the time commitment that they need. This is another O of n or n by n, and it's because we're inserting and removing stuff, adding elements to the heap, and Sterling approximation again. Should probably look into what exactly this is. No idea right now, but might not be as important. It's worth knowing that this series evaluates to this eventually, n log n. And so you have n log n. Space complexity is O of n. Even though We're using two heaps, each of size n. Space complexity is n plus n, which is 2n, but we ignore the constant exactly in complexities. And so it turns out to be n. And there's this alternate approach to use one heap, but I'm not that interested in it, and this video has gone on for long enough. Thank you for watching. Till next time.